The next talk is Context Committing Security of Leveled Leakage Resilient AED by Chandra Nandar, Jordan Ethan, Ravindra Jijorikar, myself, Iklist, and Sugata Mandel, and Sugata will give the talk.
Thanks for the introduction. I will present our work, Context Committing Security of Labeled Leakage Resilient AED, and this is a joint work with Chandranan, Jordan, Ravindra, Mustafa, Ike, and me. And this work is initiated in Asian Symmetric Key Workshop 2023. So along with this usual security requirement for AED, this confidentiality and integrity, we now require some other security like context commitment security and leakage resilient security. So in this work, we explored some connection between these two security notions and these schemes. So first, I will talk about some security notions of this committing security and leakage resilience and some other security notions. And then I will talk about two different blueprint of this leakage resilient AED schemes. One is encrypt then MAC and another is encrypt and MAC. So this is the usual CCA notion where adversary has to distinguish between these two messages. So adversary has access to 4 oracles. One is usual encryption oracle and decryption oracle. And in some cases, adversary has access to some underlying primitives, and these primitives can be keyed or unkeyed. And then adversary will ask the challenge oracle with 2 different messages, and challenge oracle will choose a message uniformly and encrypt it. And then adversary has to guess which message is selected. So with respect to leakage, for confidentiality, we have two notions. One is CCML1, where adversary has access to the similar algorithms as CCA. But in this case, adversary will get some leakages from these encryption oracles and challenge oracle also. And this leakage will be about some internal values. And then similarly, adversary has to guess the which message is selected. For CCML2, adversary will get the leakage from encryption oracle as well as the decryption oracle. And similar CCML1, adversary has to guess which message is selected. So CCML2 is a stronger security notion than CCML1. And for integrity, we have usual CTXT notion where adversary has the access to the encryption oracle and sometimes primitive oracle. And then adversary has to output a fresh and valid non-saturated ciphertext tag tuple. And in presence of leakage, adversary has the access to the encryption oracle and decryption oracle, and in both cases, adversary will get leakage about these internal variables, and then adversary has to output the fresh tuple about this ciphertext tag. So the only difference in this integrity and confidentiality notions, for confidentiality notions, usually we consider some bounded leakage, and that's for the CML2 notions, we consider unbounded leakage about the internal variables. So depending on these two notions, we have two kind of leakage resilient AED. One is grade 2, which achieves the CML2 and CCML1, and triplex and multiplex are example of these grade 2 schemes. And we have grade 3 schemes. It achieves the CML2 security and a stronger CCML2 security for the confidentiality, and TEDT and TEDT2 are two examples of these grade 3 schemes. So now, and this is the CMT4 notions. Many talks will already have defined it. This adversary has to output 2 different tuple which will lead to the same ciphertext. Okay. So now I will talk about some collision resistance notion which we need. One is the usual collision resistance notion where adversary has to give 2 input which will lead to the same output. And this partial collision resistance is similar to the collision resistance. But the only difference is there is a extra condition that some part of input has to be distinct. Maybe the other part of input can be distinct or not. And right collision resistance is the collision resistance on the right part of the output. That is this RR. For everywhere pre-image resistance, adversary has to find pre-image for every element from the range. And that's the usual pre-image resistance, but this is kind of for unkeyed functions. Okay. So but the first work on this relation between this CMT4 and leakage resilient are done by Stark et al. And they proved that this N1 scheme, which is basically encrypted MAC, this is committing under some assumptions on the components. And they also showed that this N2 schemes, which is basically encrypted MAC, is not committing, but they assumed that key for the encryption and key for the MAC, these two keys are independent. And then they gave some generic transformation from a usual A to CMT4 and leakage resilient both. In this work, we achieved some result which are different from them, but not contradicting them. I'll show that. So first, I'll talk about encrypt then MAC. So Stark et al. Proved that this doesn't achieve committing security when encryption and MAC are using two independent key. So this is a generic structure of encrypted MAC, where this encryption key and key MAC key are generated by algorithm keygen. And we proved that committing security of MAC, this encrypted MAC scheme depends on the collision resistant security of this MAC scheme and the right collision resistant security of this keygen function. So if we look at some example of this keygen function, let's talk about the first function. First function is basically it gives the encryption key and the MAC key are same. Then this right collision resistance of keygen function is basically 0. So in that case, the CMT4 security depends on only on the MAC collision resistance. And we have given some other examples where this right collision resistance advantage can be 1 also, which is basically the Stark et al.'s assumption that two independent keys. Okay. So for leakage resilient AEDs, and then with this encrypt then MAC structure follows this constant this structure where this KDF and TGF are protected against leakage, and this encryption prime and hash, these two are not these two are not protected against leakage. So these two can leak the value. And in this case, we consider this KDF and encryption prime as the encryption and hash then TGF as the MAC. So the CMT4 security depends on this has then TGF part. So next we consider some leakage resilient MAC. The first one is hash then block cipher, where the final block cipher is considered as the TGF and the input is basically the hash output of this non-saturated and ciphertext. In that case, we proved that this collision resistance of this MAC depends on the every hour image resistance of the hash and the collision resistance of the hash, and the last bounded birthday bound part comes from the ideal cipher assumption on the final block cipher. So proof idea is like very simple. Like adversary can attack for this collision resistance in 3 ways. One, he can find a pre-image of these final values for hash, and another he can find a collision on this hash. And if these two are not happening, then he has to find a collision in the final ideal cipher. So next one is hash then TBC, where this is similar as hash then block cipher. The only difference is there we have the two parts of the hash output. One part is used as the tweak and another is as input. We prove the same security bound as the hash then block cipher. And two existing schemes, TEDT and TEDT2, follows exactly this hash then TBC format, where this hash takes the 4 output non-saturated ciphertext and this public key value. This PK value is a public value, which is used basically for the multi-user security of TEDT. So here this W basically most significant n-1 bit of W concatenated with 1 used as the tweak and V as the input. So directly from our result, this every hour pre-image resistance of and collision resistance of this hash gives the CMT4 security of this TEDT scheme. And TEDT2 is similar as the TEDT, but only difference is here nonce is not the input of hash. Instead, nonce is in the tweak of the final block cipher. And TEDT2 used the 2n-bit tweak TBC. And again, similarly, that this every hour pre-image resistance and collision resistance of this hash function gives the CMT4 security. And these two, TEDT and TEDT2, both use this MDPH kind of hash function depending on this Hiroshi's double block hash. So this has achieves this FDR pre-image and collision resistance hash. And the last MAC we consider is leakage resilient MAC 1. So LR MAC 1 is similar to hash then TBC, Only difference is instead of the hash output, here we use the fixed input 0n in the final block cipher. And for this fixed input, we don't need the everywhere preimage resistance assumption on the hash. Only collision resistance on the hash is enough for the collision resistance. Next, I will talk about encrypt and MAC based leakage resilient AED. So first structure we consider, we call it KET1, where this KDF and TGF again are protected against leakage, and encryption is not protected against leakage. And input of this encryption is only associated data message and the IV from this KDF output. So we proved that if we didn't consider any assumption on this keygen function, then we need the collision resistance of KDF and right collision resistance of the encryption function, that is basically collision resistance on the FV value, and collision resistance of the TGF to achieve this 74 security of this KT1. And if we assume this left collision resistance on this keygen function, that is basically collision resistance of the KE, then we can relax the condition on TGF. Then we need only partial collision resistance, which is basically only on the FV, not the okay. And then the next part is KET2. The only difference is here nonce is the input of encryption function. And this leads us that we proved that for KET2, if we assume a right collision resistance on the keygen function, so basically collision resistance on the KE, then we don't need any assumption on the KDF. So right collision resistance of the encryption and collision resistance of the TGF gives us the 74 security. And if we consider collision resistance on the KDF, then we can relax the condition on the encryption function. We basically need the partial right collision resistance on the encryption instead of full right collision resistance. And this triplex follows this our triplex is a encrypt and MAC. But this upper portion, this KDF is the first protected block cipher and the next two block cipher. And the final block cipher is considered as the TGF, and the middle part is encryption. So for our proof, we just changed the view of this algorithm. We considered the first block cipher as the KDF, and final block cipher as the TGF, and the middle part, original encryption, along with the remaining two block cipher of the KDF as the new encryption function. So this remains the security of the triplex same, but only change the view of the triplex. So then this FV value is basically a Merkle-Damgard iteration of this hero-says double block function, and this upper AC part are the encrypting message to the ciphertext. So basically FV is the output of this MDPH part. So as we proved, the KT2A, we need the collision resistance of this hash and the collision resistance on the TGF. And for TGF, for the final block cipher, input is the fixed string 0n, so it follows the LRMAC1 structure, already I discussed. So for the triplex, we showed that triplex for the keygen function is the same key for the encryption and MAC. So right collision resistance advantage is basically 0, and indifferentiability of this MDPH basically gives the right collision resistance of the encryption function. And as TGF is the similar as LRMAC1, so we can use that bound. So we achieved this bound. And multiplex already have been presented. Multiplex followed our KET1 as a blueprint, as it doesn't take nonce as the input in the encryption function, only KDF. And multiplex proofs are similar to triplex. So in summary, we explored the relation between commitment and leakage resilient notions and proved some conditions required on the components of the leakage resilient AED to achieve this CMT4 security. And then we proved for existing scheme like TDT, TDT2, and triplex and multiplex. Thanks.
So we have time for some questions. So let's thank the speaker again and thank the speakers of this session.